Nilo, sir. No, Nilo, sir.
Yes, sir. Yes, sir. Yes, sir.
If Tandel sir is ready, to Tandel sir?
Yes, sir. Shall we start?
Tandel sir, if you are ready, then we can start, sir.
Yes, sir.
Okay.
Warmly good afternoon, one and all, and welcome to all participate in the FDP Fundamental of Geotechnical and Structural Engineering for Sustainable Infrastructure Development Program. Let's continue with today's last session to be delivered by Dr. Yogendra Tandel sir on ground improvement using stone column. It is a pleasure to introduce him. He is working as an assistant professor in the Government Engineering College, Dahod. Sir has completed his BE from MS University, Baroda in 2006, MTech from SVNIT Surat in 2008, and PhD in the year 2014 from SVNIT Surat. Sir has published more than 42 research articles in reputed journal conference. Sir has also published 3 books. Sir has guided 15 MTech students and 2 ongoing. He completed his research project funded by the Department of Science and Technology, Gujarat. I request to sir to continue this session. Thank you.
Okay, can you able to hear me?
Yes, you are hearing. You may continue.
Welcome for the last session, and topic is related to geotechnical aspect, and it is in the area of ground improvement using stone column. Now, before going to the forward, this is the outline of today's presentation. So we will discuss little bit about requirement of ground improvement and what are the different techniques available, and what could be the limitation of that techniques for Indian continent perspectively, which technique method is more suitable and which is being more used. And even just use is not enough, but in the sense design perspectively, whether guidelines, Indian standard guidelines are there or not. So among them, we'll choose one of the technique that is today, that is a stone column. And even in the stone column, you see also there is a advanced version in the stone column, one can say. Means stone column might get failed at, might not be suitable at certain situation. So there is a nowadays there is a new new tech in stone column that is called reinforced stone column. That means we need to enhance, we need to add certain extra material in stone column. So that is so-called reinforced stone column, just like a reinforced concrete column. So we will here, this is related to research perspectively. Means if you install reinforced stone column in ground for your ground improvement, so what could be the parameters that really govern the design of that particular stone column? Okay, so we need to analyze that particular parameter. So in the second point, we will discuss that part, the parameter which is most influencing, and how we can take that parameter for the design perspective. Okay, then there is a after doing so, we come to know that these are the number of parameters that are critically influenced. Okay, so by doing so, we can do certain laboratory model tests, and we can observe the failure mechanism in real manner, okay, in the laboratory scale, small scale. And once you reach the conclude from the laboratory model scale, so how that technique really behave in the field. Okay, so there are few number of load tests, that is a prototype load test is being performed, and we'll go through the results of it. Okay, so first of all, as you know, that sometimes you see we need to go for certain ground improvement. The thing is that it might be observed that your anticipated design load might be very more, that your soil may not able to carry that sustained load. Okay, your soil sometimes might be very soft, very loose, sand might be there. Okay, so in that situation you need to modify your soil. Okay, so in particularly in the last session, I mean that last in June FDP, that we have discussed about what is soft soil, loose soil, and what are the characteristics of the different soils. Okay, and what are the available ground improvement techniques. Okay, so that various fundamental of it we have already gone through it. Now in this session, we'll go through certain advanced of that. We'll choose one of the ground improvement technique and go through certain detailed aspect of it. Okay, so among them, the stone column is it is a versatile. Means just like in geotechnical engineering, I will say that standard penetration test. Okay, so whenever you go for the field report, means soil investigation report and field test, so SPT is must, standard penetration test. Okay, so based on that, all designs are governed. Okay, so here in developing country like India, okay, so we have a Indian standard code available for the stone column. Okay, so that's why I have chosen here that ground improvement technique with stone column. Now basically what to do with this technique. So here one can say that this is so called instrument that is vibratory vibroscope is there. Okay, so that is operated through the crane. Means this is to make to advance the borehole. Okay. So in this technique, vertical borehole is formed, and there is a and this vertical hole is being created, and subsequently at particular depth, means at hard strata, up to the hard strata we have to go through it. So that is also again depends on the design load. Okay, so if you kept stone column up to the soft soil level, so that might be that column will be floating, just like a floating pipe. I mean, okay, not end bearing pipe, frictional pipe. So in that manner, here we need to go to up to the certain hard strata, and subsequently filling with the cohesionless material. It is a gravel stone, and there is a size might be in the range of 20 mm to 75 mm will be there. Sometimes the upper limit might be around 75 mm. And certain times you see, if we need certain very dense, or you can say good frictional material, so sometimes with stone sand is also added, so that's frictional value will get increased. Okay, so subsequently it is filled with the cohesionless material, and again it is compacted. So at the ground level, up to you to reach it up to the ground level. So here in this manner, this is the for the single stone column only, but for your whole your site, okay, whole plan area, you have to go for a number of stone column, that or might be for the embankment stone column, okay, or might be for the your or you can say raft, below the raft the stone column is required. Okay, so or most favorable most of the cases stone column you see normally employed for the embankment foundation, then oil storage tank. So in the India, you see, most of the cases, the number of case studies are available with this stone column. And uh, if you go through New Mumbai, then Hajira and Vishakhapatnam, that means all coastal area where we have you see oil storage tanks are there. Okay, so strengthening of that particular all coastal the area, okay, where the stone column is normally being used. Okay, so because this is the versatile and known technique, and for this technique we have a Indian standard available, that is IS 15284, and in the subsequently in the lecture we will see how to design stone column also accordingly IS 15284. Okay, so here these are the number of techniques, okay, available, starting from this dynamic compaction. Now here, in this technique, this heavyweight tandem, so this weight might be in the term, it might be reached in the amount of might be 10 ton, 1 ton, okay. So depending on the project, depending on the soil condition. So what happened, this heavyweight tandem is they just lifted at up to the height of 3 to 4 meter, and it is just drop. So what happened, this kind of drag is being created, this drag is formed. So this is being filled up again, and it is again then compacted, and it is get level. So what happened, due to this heavy weight, this loose sand will get compacted. So remember, this dynamic compaction is for a cohesionless soil, okay. So it actually compact, it densify the soil, okay. Now again, you see in this technique, you can see here this large weight is required, heavy crane is required to lift this tandem. And you see, if there is a nearby structure is there, so due to vibration, that structure, any buildings might be there, so that might be crack, okay. So due to that vibration, so that is the one limitation one can say regarding the dynamic compaction. Then move to the right side, there is a prefabricated vertical tree. Okay, so these are all are the deep ground improvement technique, not on at shallow depth. It is not for the, you can see, simple footing or might be for a road point of view. Okay, so that is a deep seated ground improvement technique, in the sense that the soft soil is available at very large depth, and for that, if you want to go for the ground improvement technique, okay, so these are the techniques. And second one, that is your prefabricated vertical drain. Now in this technique, basically it is for the cohesive soil. Okay. Now in cohesive soil, basically we have a issue regarding its water content. When we have a very high water content, so what happens? It will get consolidated. Okay, and that consolidation phenomena will take large, means it is a long phenomena, means it will take around 10 years, 15 years if you don't accelerate that consolidation. So here, basically what to do here, this vertical drain means just like a it's just like a flexible pipe, one can say, but in the form of corrugation. Okay, so this install at the suitable interval, that is around 1 to 1.5 meter interval. So that's depending again on the design perspective. Now here, so once this all drain are being installed, these all are connected with pipe, and heavy this embankment, there is a surcharge is being applied. So what happened, due to this surcharge, this clay will get consolidated, in the sense it will drainage will occur. So what happened, we artificially drain the soil, we artificially consolidate the clay. Okay, so the clay which will take a consolidation time around 10 to 15 meter without improvement. So what we will do, we accelerate that consolidation. In the future, the consolidation that is going to have, okay, we accelerate that consolidation within around 6 months. Okay, so what happened, that all soil will get consolidated. So then this one can say this ground is get improved. Okay, so again one can say this is the long phenomenon. It will take a couple of months, actually at least around 6 months to get consolidated. Then clockwise, we have a deep mixing technique. Now in this deep mixing technique, basically it is originated in Japan, and then in China also it is being used most. So that all countries are usually very nearer to this Japan, it is the coastal area. So what happened in this technique, this machine mounted auger is there. Okay, so it will get deeper in the ground, and after reach to certain depth, okay, what happened, this through this particular auger, there is a nozzle also there. So your cementitious material might be cement, lime, or mixture of both. Okay, so that will get penetrate in the ground at a deeper level. Okay, and after reaching that particular depth, so this auger will get lifted slowly. So what happened? This cementitious material means here soil will not taken out, just like a stone column. Soil will not taken out, but soil it is remain as it is. But it is now you are doing the augering, so it will get loosened, and this cementitious material will get penetrated in the ground. So subsequently it is lifted, and with the cementitious material, this column will be formed. So this column means in the sense the cementitious column, or you can say lime column, one can say. So that will be there is a having a mixture with soil. Okay, so the column ultimately which being formed, that is having high stiffness, and at particular side there are a number of different in the plan area, number of column. So ultimately you reinforce the ground, okay, with higher stiffness material. Okay, so here in this technique also in India very few case studies are available with this deep mixing technique, because it is a certain sophisticated equipments are required. Then again clockwise there is a grouting. Okay, now if you have a fissures, means cracks in the ground, uh, okay, when you have a sandy soil, okay, so in that fine or medium sandy soil is there. Okay, so in that case we can do this grouting. So in the grouting, that is vertical pipe is there. So through this nozzle, that is a grouting material being injected. Okay, now and this grouting material, it will get filled in the cracks, and it will strengthen the ground. Okay, so ultimately at various points this grouting is being carried out, and ultimately this reinforced ground having a higher load carrying capacity. So in this grouting we are injecting certain chemical, that is either cement or lime, or calcium chloride might be there. So what happen, it will react with this clay soil. There is a cation exchange will occur, and ultimately it will strengthen the ground. Now there is a chemical process, that means it will take certain times. Okay, so there is a normally in the cement we required curing, there is around minimum around 28 days. Okay, 7 days is must. So here also, but apart from this all ground improvement technique, you see there is a certain there is each having certain limitation. Okay, so apart from this all ground improvement technique, so why we need to go stone? So because there is a certain environmental constraint is there. Okay, so there might be certain obviously we need certain economy in the project. Okay, so say for example, if you consider with dynamic compaction, okay, so it will can't possible in the urban area, means when we have a very near structure, so there might be cracks develop in the structure. Okay, likewise this PVD. Okay, so PVD, once in the PVD, what happened, we just this prefabricated vertical drain installation, it will not serve the purpose. We need to apply certain surcharge, and that surcharge will long for around 3 to around 6 months. Okay, and then again we have to unload that surcharge. Okay, if it is an embankment, that doesn't matter. So it is a time consuming matter. So by and you see this stone column technique is a very old technique, and you see even with your simple piling rig equipment, one can do excavation, and with this baler also one can do the compaction. Okay, if your soft soil strata is not deeper one. Okay, if you having a want to improve the soil up to the say for example maximum around 8 meter depth, so by this rig piling rig, you can do the construction. So it is a apart from other techniques, it is a simpler one. Okay, and once you do the stone column, after installation of stone column, you can directly apply the structural load on that. You can do the construction once the stone column is being done. Okay, so that's why it is a faster method also. Okay, so that's why one can say this stone column, that's why it's being very important one. And you are surprised to know that first stone column, you see, being applied for the foundation of Taj Mahal, but not like the way in which we are having stone column technique that which we are having, but in the that period, you see that vertical dig is being formed. I mean, the foundation, at the particular foundation of this particular Taj Mahal, there is a vertical dig is being formed at the shallow depth, okay, at a number of locations, and then structure is being constructed. Okay, so that is available at particular this web. There is a citation for this. Now, here, when load is being applied on stone column, so how it behave? Okay, so basically you can visualize this. There is a when load is applied, so what happens? This upper portion of the stone column, which is actually granular material, it is not a rigid one. So what happens? It will get bulge, means there is a lateral deformation occur, and this lateral deformation occur around up to the depth of 4 times diameter of the column. So what happens? The load carrying capacity of this stone column, so is basically depends on lateral pressure provided by the surrounding soil. Okay, so if this soil is being very weak, okay, say for example this soil clay having a undrained cohesion, there is a cohesion that is around 10 or sometimes 15. Okay, so in that situation, what happen? It will get bulge more, or the chances is there that that stone part and this clay material will get penetrate in this stone column. So this granular material, it will now lose its frictional value. So once frictional of the particular stone column material get reduced, so eventually its bearing capacity will get reduced. Okay, and this stone material might be get punched in the surrounding soil. So these are some of the limitations which are observed in the past. Okay, so even you see most of the design charts which are developed. Okay, say for example this Thornburn. So you can see here that is a this chart is applicable with cohesion value around 20 kPa only. Then in Greenwood, okay, so there is a limitation, that is a you can go stone column up to 20 kPa. Okay, then in the 1979, there is a small GEC here developed this design chart for load carrying capacity of stone column. This stone column is also called as a granular pipe. Okay, so here there is an undrained cohesion value. So you can see here. So what here is told that stone column is unstable after this lowest cohesion value. There is below 15 kPa, your stone column might not be suitable. Okay, and beyond 50 kPa, actually we don't require this stone column. It is not economical one can say. Means it is having good strength. Okay, so all these previous theories and previous design charts, okay, so that talks about cohesion value around 15 kPa. So this is the one of the limitation that one can say that stone column might not be favorable in this kind of soil which is having undrained cohesion value around 15 kPa. And I have collected some of the certain case studies where actually stone column get fail or not perform satisfactorily. Okay, so these are the very rare case studies available on net, so you can read it. This available. First case study is that is done by McKenna in 1975 in Southwest England. So basically the purpose for that construction is to carry out the embankment having height up to the 9 meter. And you see, around 20 centimeter depth, there is a soft alluvial soil was observed. And based on design, they carried out come to with column diameter 0.9 meter and having length 11.3 meter. And once you see that embankment reached to 7.9 meter, okay, they have collected certain readings related to settlement with settlement plate. Now you can see here this graph is settlement versus depth, means depth wise vertical settlement. So this is the settlement at the ground level. Okay? This is the settlement at the vertical at the ground level. Now you can see here this is the graph with untreated end, and this is with stone column. Means the where stone column is being installed, where settlement is being taken, and you can see here actually a stone column portion means where stone column is being installed at particular embankment section, settlement is more compared to untreated portion. Okay, the reason behind that was that the squeezing of soft clay into stone aggregate. So as I have previously told that in that kind of soil which is having undrained cohesion less than around 15 kPa, okay, so this soft soil clay might get penetrated into stone aggregate, and its stone, there is a frictional value get lost. Okay, and what happened, you are in that particular site vibrofloat instrument is being used. That means when you go through vibro-flotation, so due to that vibration, the soil get remolded. Okay, because this is having a soil, it is a 15 kPa clay soil. So soil get remolded and its undrained cohesion after that vibration get reduced. So that's why installation of stone column doesn't affect on the strengthening of the foundation. Okay. Now this is the case study reported by Greenwood and Schumer in 91 and 1993. That is near to Bombay, and this is for the LNG storage tank, and you can see here that SPTN value, you can see here up to the depth of 11 meter. So at the 11 meter depth we have a good soil having a gravel, and this SPTN value after that depth is around 29. So stone column design up to this level, and you can see here the SPT value here. So on an average it is around 3, on an average around 3. So if you calculate that cohesion value to the SPT or perform Van shear test, so this undrained cohesion value is very less. It is around 3 to 30, very maximum value is around 30. At somewhere location it is around near to 3 only. Okay, so at that particular site also this stone column being applied, having diameter 0.9 meter and length is around 10 to 12 meter, being vibroflotation technique is being used. Okay, now once this reach, after as this that LNG tank is being filled, okay, with oil, so what happened, this kind of failure is being observed. There is a, you can observe this, you can see here this kind of heaving is being observed. Okay, so and there is a certain cracks is also there. Okay, so there is a totally one can say catastrophic failure is being observed. Okay, and again the reason for that, for the same, that this kind of vibroflotation when being installed, the stone column is being installed with this vibrofloat, okay, having soil undrained cohesion around nearer to around 3 to 15 kPa. So it remold the soil. Okay, and that particular stone material, again I told you that clay might get penetrated into stone column material. Okay, so same the behavior which was observed in 1975 that we have mentioned in McKenna theory, that case study. The same such kind of failure is also being observed. Now remember one thing, stone column doesn't, it is not a magic say that you install stone column and you will get the safe bearing capacity around 10 times, 20 times, 50 times, not like that. Okay, so maximum stone bearing capacity improvement is being observed around yeah, 5 to 8 times. Okay, maximum that much amount can be possible. That is a, you can see here. So that with respect to undrained cohesion, okay, so maximum ultimate capacity can be observed around 25 times. So safe bearing capacity, safe carrying capacity that is observed, that is around 8 times. So here that is one of the reason that is that bearing capacity is not reached, means not reached in the sense that vibro flotation that should not be employed, that remold the soil. Okay, then one of the failure related to embankment that is observed in 2004 by Gu and Tan. This location is being not given, but it is mostly in the southeast south area. It is in Asian country, might be in the Indonesia somewhere. Okay, and at that particular site, the undrained cohesion is around 8 to 19 kPa, and sensitivity observed is around 5 to 12 kPa. That means if you remold the soil, so that undrained cohesion get reduced around this much value, means 12 times there is a reduction in undrained cohesion with vibration. Okay, now here basically global failure is observed, means slow fail. There is a, it is not a basically one can say bearing capacity is used, but there is a global failure was being observed. So you can see here this whole mass gets slide. Okay, so that's why you can see here this is the basic initially top level, and this much subsidence is observed here, and there is a heave is being observed here. Okay, now here the thing was that stone column being designed for a basically considering bearing capacity perspectively, means for a given soil, you see this much diameter and column is being length is being derived based on the design theory, but they don't have taken care for the global stability, means slope stability point perspectively. Okay, so that's that one of the reason. And if you go through the this design theory, you see you have to take care of that theory, means there is a certain limitation of different theory. IS 1584 talk about different methodology, certain theories, you see based on the particular L by D ratio of the stone column. So there is a particular theory having certain limitation. Okay, so depending on your project site, one can go through the particular theory. Okay, now this is the again embankment failure in Queensland in Australia. O has reported these studies in 2007, and you can see here that again cohesion values are near to 5 to 20 kPa, and stone column being having a diameter around 1 meter. Okay, so you can see this graph, that is nomenclature for this graph is, you can see here there is a no ground improvement, there is a this line, then the square is for stone column installed at 3 meter interval, then installed at 2 meter interval. So you can see the settlement which is being occur. Okay, actually consolidation settlement which is being occur. So you can see here at that particular around 120 days, 130 days. So it is value are very near to each other. Means there is not improvement observed even using stone column. And reason which being postulated here, there is a weakening of sensitive clay during stone column installation. Okay, so that clay get remolded. So once clay get remolded, what happen? Its cohesion will get reduced. The cohesion value here that is being observed, that is a uh, that is in the virgin clay, in virgin soil. Okay, so after that this vibroflotation being used, so your that clay get remolded and its cohesion get reduced. Okay, so that is the one of the reason. And again that is the excessive bulging of stone cone observed, because as we have seen in first couple of slide, that if you have a more amount of bulging, more lateral, okay, so that will be stone column might be squeezed into clay. Okay, so your formation of the stone column might not possible. Okay, so these are the a couple of three reasons which are being postulated in paper. Okay, so that means we should have a certain solution of that. Okay, so way back in 1989, particularly in India, for oil storage tank, you see what happened, that you can provide skirting, means a skirting of individual stone column, or might be total group of stone column. Okay, so here skirting in the sense axis is skirt this axis is just like a peripheral, you can see in the ring type construction will be there. Okay, so throughout the, and you can see here it is not provided throughout the depth, but where stone column bulging is predominant. Okay, so that stone column bulging is there, bulging is observed, might be around 4 to 5 times diameter of the column. So up to that you have to provide stone this skirting. Okay, then there is a one laboratory study might be available, study is available. In that this reinforcement means this nail is being peripheral nail ring is being constructed, means this in the plan you can see here in this way. So this is vertical number of bars nails are there. Okay, so it is somewhat like a this skirting, but it is with this reinforcement itself. So what happened, this it might be possible that when we have a very waterlogged area, this reinforcement get corroded by virtue of time. Okay, so that is and it's regarding its installation also there is a issue. This is related to laboratory scale test only, so there is a no case studies available related to this method actually. Then just like a sandwich, okay, we might have this horizontal reinforcement. Okay, this horizontal reinforcement either in the form of geogrid or might be steel disc. Okay, so what happened, this material will get confined, this stone column material will get confined, so it will not get you see bulge. Bulge. Okay, so this is one of the technique that is being in the past 10 years, might be 10 years this technique come into picture. Now here you see uh, here again that is a horizontal disc need to provide. So there is a certain in the field also this kind of case studies is not still available, where this kind of the this horizontal in the form of geogrid it is provided for the particularly for the stone column, because there is a certain construction issues are there. Okay, and today that we are going to discuss is this reinforced stone column. There is geosynthetic reinforced stone column. So here this white color material is geosynthetic. So that might be geosynthetic. It is a planar material. It is a material might be either polypropylene or polyethylene. Okay, so depending on the design. So this is in the form of cylinder. That is a cylindrical skirt type. Okay, so this provided surrounding to stone column. So what happened? This material will not, stone column material will not directly come into contact with surrounding clay soil. So you reinforce your stone column. Okay. So what happened? This peripheral, this geosynthetic material. So it will provide extra confining pressure to this stone column material. So what happened? It will multiple advantages will be there. So it will provide additional confinement, additional lateral pressure to the stone column. So its load carrying capacity of the stone column will get increased. Okay. So here, this is our target today. We will discuss about this design of reinforced stone column. So before that, we will go through what are the different parameters, factors which really affect this design of stone column. Okay. Now, first, this kind of stone column, reinforced stone column, is applied in the for an embankment for height of 5 meter for railway embankment in Hamburg in 1996. Then in large scale in the sense around 50,000 column, this stone column is being applied for at the site of Airbus A380 production in Hamburg, Germany. Okay, so this site is very near to this river. So here this dike embankment is being constructed here. Okay, so and this is the your Airbus A380 production site. So this for this embankment. Okay, at embankment height, that is depending on the design, it reach around 5 meter to 10 meter. Okay, so for strengthening of this foundation of embankment, this geosynthetic encased stone column, or you can say geosynthetic reinforced stone column, was used in 2002. Now, for installation of this technique, we have two methods. There is a displacement method or replacement method. So in the displacement method, we don't take out the soil, just like in the replacement, just like auger. Okay, in the replacement method, we do augering, means soil is being taken out. But in the displacement method, so what happened? This pipe, that is a vibratory pipe. You see, it will get inserted in the ground. Okay, so this is the schematic diagram for the same. So this casing, okay, with a closed end, there's a flip is there here. Okay, now flip is now it is open. So either geosynthetic can be wrapped around this casing, or might be in this particularly this might be inserted afterwards in the borehole, just like in this graph figure. Okay, what happen once you reach to particular depth, this flip will get open. Okay, now through this hopper you can insert, you can just hopper, you can insert in this stone column material. Now here, this is the schematic way. So up to particular depth, okay, this casing is being installed. Then this sleeve, it is just like a your socks. Okay, this is in the form of cylinder. Okay, the both way is open. So it is being just kept at particular, just like a reinforcement cage. Okay, then stone column material is being added, and it is subsequently compacted. So what happened? This flip will get open, and you just add the material, just compact, and just remove this casing, and ultimately you will have this kind of the full stone column. So this is the displacement method. Means initially this flip is closed. So what happened? As we insert this casing, the soil material get displaced surrounding horizontally. Okay, then in replacement method, when uh, uh, you have soil certain, you can see little bit stiff or medium type clay is there. Okay, in that situation, what to do? This casing is being inserted, and with auger this soil is being removed, and then after this reinforcement sleeve is being inserted up to the design depth. And once you compact, what happen, the reinforcements in the machinery, there is a technique is there, so that end will be fixed at upper portion. Okay, so it will not get down. So once you compact, what happen, this reinforcement will take a shape of the cylinder. Okay, once you do the compaction. Okay, so ultimately again, then after, it is the same way as displacement method. Okay, so if you have a you see very soft soil is there, so you can go for this particular displacement method. Otherwise replacement is there. So sometimes it's depend on the availability of the instrument is also there. So this replacement method, you can see that with your piling equipment. Okay, so just like an installation of the pile, so with this piling rig also, one can go for this kind of technique. Okay, so that piling ring is sometimes it is a multi-purpose piling ring rig might be there for the installation of the column, stone column, and for the pile also. Okay, now here what we will do here, that we take certain embankment, and we analyze that performance, that is the behavior of this embankment, how this embankment will get behave with this installation of this geosynthetic reinforced stone column. Now here, so what happened, this is the embankment having height 5 meter. It is a symmetrical embankment, so just one half symmetrical portion is being taken, and having height 5 meter, width 18 meter, and soft clay being taken up to the depth of 10 meters. So at this particular depth, we have a hard strata. Okay, and software which is being used, there is a Plexus 3D, so that will model this stone column and embankment. And water table is being observed at this particular ground level. That means it is a very soft soil, one can say, very high water level. So displacement with the symmetry, one can say this displacement will allowed vertically for left and right one. And at the bottom there is a hard strata, so there is no displacement allowed. It is a vertical and horizontal displacement will not be there. And regarding the hydraulic condition, hydraulic boundary condition means when you apply the load, what happen? Pore water pressure will be generated. So what happen if there is a sand? Okay, if here is in the field, if it is a sand here, then water will drain through this. Okay, but here stiff clay is being taken. So water will be just drain out from the upper portion. Okay, so that's why phreatic line means water table is observed at this particular depth also, depth at itself. So here this boundary is kept impervious. This is very far boundary, and this is a symmetrical boundary. So this all three boundary are taken as a cement impervious. So water will come out through this upper horizontal ground surface itself. Okay. Now before going for the any, you see, any software model, so you need to validate your model. Validate the model in the sense that whatever the material property, whatever the model that you are taking for your research perspectively, whether it is a Moore column model, linear elastic model, okay, might be modified chem clay model, hardening soil model. So which model you have to take? Okay, so so before going for any model, adoption of any material model, so you have to validate your material model. So here one of the study from Mbili and Gandhi, reserve properties being taken from them experimental data. So if you model in the Plexus 3D of the same, the data with this paper, that is of experimental data obviously, So you can see here this is a graph, and the graph which is being observed with Plexus 3D. So there is a very trend is very similar. So one can say that material model that we are going to have in for a particular research, there is a that can be used for the further. Okay. Now, as you know, that the material model which is being adopted for a stone column, embankment, and clay, that is a Moore column model. So, because this Moore column model is being validated based on the experimental data. Okay. Then, as you know, embankment. You see, embankment is not constructed rapidly. Okay. So it is not layer-wise construction will be there. So each one meter layer of embankment is being constructed for 30 days. Then again after 30 days, consolidation period was allowed. So what happened? Once you applied one layer, it means you do construction for a particular layer. There is a 1 meter, say for example here, and you need to allow the consolidation to have consolidation of that particular soft clay. Okay, so if you do construction of the embankment, say for example 5 meter embankment suddenly, so what happened? There is a large amount of the pore water pressure will be generated, and that will create failure of your embankment at the construction phase itself. Okay, so that's why we have to do the construction in stages. Okay, so these are the different properties taken for the parametric study, and you see each property is having identical properties in the sense that the properties are adapted based on the previous studies, based on the previous field data. Okay, so here you can see the spacing of this geosynthetic reinforced stone column taken varying from 1.5 to 3 meter. So normal in the field also this spacing is normally adapted, and you can see here there is an asterisk symbol is for the particular benchmark case. Benchmark in the case in the sense, say for example, at here you take for particular model you take spacing 2.5 meter. So or other parameters now will get keep constant. So at a one time you can vary only one parameter only. Okay. Then elastic modulus of stone column material range from 30,000 to 50,000 kPa. Okay, at the high up to the higher level, this stone column material modulus is being taken, and then elastic modulus of the embankment fill material is taken 30,000 to 40,000 kPa. Then height of the embankment reached from 5 to 10 meter, and thickness of the soft clay. So soft clay might be at a shallow depth, might be 4-5 meter, 10 meter, 15-20 meters. Okay. Then stiffness of geosynthetic. Stiffness means it is a it is a particular modulus of geosynthetic material. One can say. Okay. So stiffness means it is a tensile strength upon weight of the that particular material. One running meter tensile strength upon unit length of particular that geosynthetic material. Okay, and this value are, you see, it is normally adapted in the prototype, in the field, in the construction industries. Okay, so that all values are being taken. Then basic properties for the soft clay, stone column, and embankment fill. You can see here there is a permeability is very essential. Yeah, if you don't employ permeability, so what happens? Consolidation, that consolidation you don't in the output parameter you don't get the parameter related to consolidation. There is a excess pore water pressure, that values will not be there. I mean, that is not a right one you observe. Okay, so obviously this all parameters is based on the previous studies. Okay, now here we will see that what is the effect of all different parameters on particular settlement of particular embankment, and then it's a lateral deformation in the sense stone column, how much stone column will get bulge, and how much pore water pressure will be developed. Okay, so by studying all these parameters, say for example at particular case pore water pressure is observed around 16 kPa. Okay, so what happened? Pore water for 16 kPa vertical pore water pressure will be generated. So your surcharge will be sufficient of that. Means if surcharge is not that much enough, so water will just, I mean, embankment will get collapsed. Okay, so here first parameter that is studies, it is spacing, S by D ratio, spacing to diameter ratio. Now here it is the distance from symmetry axis. Okay, and this point, this higher point, it is related to stone column area, stone column middle point. Okay, and this is lower point is related on the soil, on the soil. So if you plot this reading, that is an average settlement on particular ground surface with S by D ratio. So you can see here, so as this S by D ratio increase, your settlement will get increased. And here in the third figure, settlement improvement factor is being derived here. Now settlement improvement factor in the sense settlement without treatment to settlement with reinforced stone. Okay, so obviously settlement with without treatment, that will be constant value, and settlement with reinforced stone column. So as obviously this value should be lower, settlement with reinforced stone column should be lower. So eventually this SIF value should be more. SIF value should be more. So when you will get more SIF value, if you will have a lower S by D ratio. Okay, so if you know, so in this SIF, if you know, if I will give the value of SIF, say for example 2, and you will have a settlement without treatment, okay, of virgin soil. So based on this relation, you can find out the future settlement of this reinforced stone column. So that equation that we will see later on. Here you can see here, if you go S by D ratio from 3.75 to up to the 2.5 meter, so there is a drastically changing settlement reduction. There is around 50% settlement reduction is being observed. Okay, and here this is related to excess pore water pressure. Means whenever in the waterlogged soil, when load is being applied, such as load is there, so what happens? Water will come out from the voids at particular rate. So that is called pore water pressure. Okay, so as you can see here, as S by D ratio get increased, means stone column installed at far distance. So what happens if you install stone column at a far distance? Then you might reach into economy, but what happens? More amount of load now will transfer to the clay compared to at smaller S by D ratio. So what happens? More amount of the load transfer to the clay, so there will be more amount of the pore water pressure will be generated. And as you will have a higher S by D ratio, means higher spacing to diameter ratio, so there will be a larger amount of bulging will be there. So you can see here S by D ratio 1.87, it is a deformation, there is a bulging around 15, and the value with S by D is a 3.75, so you can, it is nearer to 60. So you can see here there is a large reduction in bulging is observed, and maximum lateral deformation you see here, this is the maximum value for a particular S by D ratio 3.75. This is the maximum value for you can say 3.12 S by D, and again for 2.5 S by D ratio, this is the maximum value. Means at along the depth where you can reach maximum value, so that depth comes out to be 3.75 times the diameter of the column. Okay, so that's why in the previously in the various in the previous slides we have seen that bulging is observed around 4 times diameter of the column. So up to that much depth, okay, so your material should be having a good quality. Beyond that, means up to that much depth, that load is being transferred. Okay, and regarding the stone column material, influence of elastic modulus of stone column material. So this is the remember, this is the reinforced stone column, means stone column is reinforced with geosynthetic. So you can see here, if you this is a very interesting phenomenon. You can see here stone column material having a modulus 30,000 and stone column material having a modulus 45,000 kPa. So it will not change settlement much. So it will reduce settlement around 8 mm. You can see here in this graph, average settlement will not reduce by modulus of stone column. So because the thing is that this reinforcement material means the stone column which is reinforced with geosynthetic, so that will provide additional hoof stresses. That will provide additional confining stress. So that stone column material is just confined in between. So that influence of stone column will not reach compared to this geosynthetic peripheral material. Okay, so that's why the practical benefit of this is that you can go for the lower quality of stone column material when we go for the geosynthetic reinforced stone column. Now this conclusion is not valid for normal stone column. So in the normal stone column, what happens? Stone column is not confined. So it will just it is having a boundary. It is having directly directly interconnected with the clay. So it will soil is being, if it is soil is being loose, soft, so that stone column material will get punched in the stone surrounding soil. So in here, this geosynthetic is being confined by this stone column material. So that's why we don't need to go for the good quality stone column material. Okay? So this is the very you see important conclusion that one can have field perspectively. So here you can see here that when you go for this stone column with geosynthetic reinforced stone column, so what happens? This arching phenomenon will be developed. In the sense, more stress is attracted. You see, more stress will be attracted to this stone column, because this stone column material now having a higher stiffness. So that higher stiffness material will attract more surcharge stress. Okay, so that's why that on there will not be stress more as compared to stone column. So this material load will not come on clay material, so it will not get settlement large. Okay, and again you can see here there is not much more change in pore water pressure as well as the bulging of the stone column. Now again, same phenomenon is being observed for embankment fill material also. Okay, so embankment fill material having a modulus 30,000 to 40,000 kPa. So you can see here there is not significant change in settlement of your embankment at the ground surface. Okay, so here because your the foundation reinforced with this stone column, it is a having a higher stiffness. Okay, so if you go for a good stone column material also, so surcharge actually does not going to get changed. Means if you have a higher frictional material, overall embankment height is same, and just you are changing the stone column material, I mean your embankment material, so it will not enhance the much settlement. But obviously if you go for the good strength material of embankment, in that case that is a stability of, that is a global stability of this particular embankment will get enhanced. Okay, but settlement perspectively, this we don't to go for higher modulus material. Okay, higher modulus material. Now let's see the influence of geosynthetic stiffness. Means this J value. Here, J means it's the modulus of geosynthetic material. Now, in this graph, we have used non-dimensional parameter, means which incorporate the geodetic stiffness, diameter of the column, as well as the modulus of clay. Okay, so this is the non-dimensional parameter, and now we will see later on how this non-dimensional parameter is being used for the development of equation. It is a settlement improvement factor equation. Okay, so now here, as this material strength will, there is a geosynthetic material modulus will get changed, so you will having a lower settlement compared to there is a geosynthetic material having a lower strength. Okay, so here settlement improvement factor, that is a reach from this 2.5 to around 4.5. So at least around 2 times, 2.5 times more when settlement will get reduced. Okay, and you can see here that settlement with lower modulus, okay, settlement with lower modulus will having a higher higher pore water pressure. Okay, so means if you go for a higher stiffness of reinforcing material, your stone column will be more stiffer, and once it is more stiffer, it will attract more surcharge, and the stress which is going to have on clay will get reduced. So once it will get increased basically, and if you have a more stress on clay, that means there will be a more pore water pressure will be there. Okay, so in the stone column with lower stiffness material, more amount of load transfer to the clay, and we will have a more pore water pressure. And you can see the same through this principal stress. Okay, so you can here this geosynthetic having a modulus 500 kN per running meter, and this is with 8000. Okay, so you can observe the with this picture at here at the ground level. So you can see here that the stress which is transferred with 500 kN per running meter geosynthetic stiffness, and the stress with this 8000 kN per meter running meter stiffness. So you can see here the principal stresses means the load which is transferred at particular level on the clay, it will get reduced. Okay, with a larger stiffness material. So here with lower stiffness material, more load will be transferred here. So on the clay, more load means more pore water pressure will be there. So just like this is the value. Okay, and again that is influence on the bulging of stone column also. Okay, so here this is the graph with blue, that is a J with 800, and this black is J with 8000. So if you have a larger stiffness, okay, if you have a larger stiffness modulus, that is the tensile strength of geosynthetic, so there will be a much more amount of hoop stress will be generated. Okay, so hoop stress, that is a one can say there is a 2T upon D. This is the hoop stress equation. So if you have a higher tensile strength of geosynthetic material, so you will have a higher stiffness, so higher confining pressure. So if you draw on a plan, so this is the stone column material, okay, and this is the geosynthetic. So what happened? There will be more hoop stress will be developed. So this will prevent. So this hoop stress will prevent outward bulging of this stone column. Okay, so that's why when we have a more stiffer material, more stiffer geosynthetic, we will have a very less bulging. Okay, then influence of height of embankment. This is the obvious. That is a if you have a more height of embankment means we will have a more surcharge load. if you have a more surcharge load, that means more height of embankment, there will be more amount of settlement. And you can see here just 5 to 7, if you go for from 5 to 7.5 meter height of embankment, so this settlement increase almost around 40 to 50%. Okay. Then again pore water pressure. So you can see here, as there is a more height, means there will be more load transfer on the ground. So more the load, there will be a more amount of the pore water pressure. Okay, so in the field you have to observe it, means at particular layer of embankment construction, you have to actually study when you have to go for this embankment design. So how much amount of maximum amount of pore water pressure, upward pore pressure going to there. So even based on that, you can do construction. So you can do construction in a one phase, in a one just in a 5 meter embankment can't constructed in a one layer. So that should be a step by step. Okay. So here again with more higher the embankment, higher will be bulging. Now let's see that what is the influence of length of fully reinforced end bearing column. Means here up to this stage, our stone column is end bearing, means it is raised on hard strata. It is not a floating column, one can say. Okay. So you can see here that as this end bearing column get, length of the column get increased. Okay, length of the, or you can say thickness of the soft clay get increased, your settlement, average settlement will get increased. Now this behavior it is not in line with previous studies, and the previous studies that observe that at a particular L by D ratio, this settlement, or I mean that behavior of the stone column will remain. Now this study actually is based on the single stone column. Okay, that is not a stone column is not analyzed in the form of embankment foundation. So just one stone column is being loaded, and this conclusion is being drawn. So this is applicable when we have a single stone column only. So whatever the conclusion, whatever the that the outcome which is observed based on the single stone column, so same concept principle may not be applied for the group of column, for the one can say design of embankment. Okay. So in that previous study, they observed that up to the L by D ratio. Okay, so this means length, that is a particular L by D ratio. There will be, after that there is not appreciable change in behavior of stone column. Okay, so again if you have a higher the soft clay thickness, you can see here this pore water pressure will get increased more and more. Okay, and here stone column is up to the depth of 5 meter, then here it is up to the 10 meter and this 15 meter. So you will have a more and more amount of bulging will be there. Now this is the one of the important parameter that is come in mind, that does it we require reinforcement length geosynthetic up to the full depth of the column, or we can curtail the reinforcement length. Thus we need to provide up to the specific diameter of the column up to a certain length or not. Okay, so here as you can see here, as this reinforcement length will get increase, okay, this settlement will get decrease. Now previous study says that we need to go for reinforcement length around 40, around on an average 4D based on the previous studies. But that previous studies, that means that study is based on the single stone column. Analysis are being carried out based on the single stone column. So you can't design stone column with a reinforcement length based on the 4D length, based on the single stone column analysis. If you provide the 4D length for the embankment also, so then in that case it will not serve the purpose. So that's why it is required to study the reinforced stone column for embankment foundation. So whatever the conclusion which is being drawn from the single column, so that same philosophy can't be applied for the stone column width in a group. Okay, so you can see here there is a reinforcement length get increase. So here it is reinforcement length, it is being nomenclature in the form of diameter of the column. So you can see here reinforcement length of 12.5D. So there is a this one. So as you go for higher reinforcement length, you see that is a what happened, more amount of this load will transfer at a deeper level. Okay, previously what happened, if it is a single stone column, simple stone column without reinforcement, what happened, the bulging will be happen at the top portion itself. But here what happened, this material will get confined the stone column. So whatever the stress transfer that mobilize at the top of the column, it will transfer at a deeper level. It will transfer at the deeper level. So this is the advantages of this geosynthetic reinforced stone column. And you can see here at this level, this is the red one is with RL reinforcement length 12.5D, means at the full reinforcement. So at the full reinforcement, you can see here maximum bulging observed at this depth. But for with 4 times dia, means you can see here the maximum bulging will not observe at particular same depth as of full length, but at the junction between this reinforcement and this stone column material. So at this depth, at this level, you will observe this bulging. Okay, because here material will not confine at this location. So that's why you will have observed this failure here in the stone column. Okay. Okay. You can see here the stone column with full reinforcement and stone column with partial reinforcement. So you can see here that the maximum bulging can be possible up to this depth, and with 4D reinforcement length, so you can observe that bulging at the junction of this reinforcement and unreinforcement portion. Now here it is a influence of length of column. So length of column in the sense, here we are taking H, there is a thickness of the soft clay constant, but now we are changing length of the column in the sense floating column. So previous study is based on this end bearing column. Now we change the length of the column, means floating column. Okay, so obviously if column is being floating, so the settlement will be more. Okay, so you can observe in the same here. If your column is floated, means here 12.5D, there is a this one 12.5D means this red one. So you can see here 12.5D means end bearing column. Okay, so that is a this one, and there is a 4D, there is a this value, it is a floating. So this all three are floating. So you can see here compared to end bearing, floating column having a very large settlement. Okay. And same thing is observed here. So you can see here that is a the with floating reinforced column. You can see here this is with respect to end bearing column. Okay, this is the value of pore water pressure, and you can see here if you provide the reinforcement length up to 4D, so you can see there is a drastically change in pore water pressure. There is a from 10 to around 70 kPa. That is a 7 times pore water pressure will that is increased. So that pore water pressure will go upward. So if you don't have enough surcharge, so what happened, that embankment will get collapsed. Means there is a failure of embankment will observe. Okay, and same thing here also with lower reinforcement length with a floating column, you will observe this kind of failure. Means there is the bulging is there, but it will get punch also. Okay, so this is the you can see here this 12.5D, and then there is a length of the column 4D up to the 4D. There is a short column and one can say long column. So short column, there is a this one. So it will get punch. It will get punch. Okay, there is a certain amount of the bulge will be there up to the certain mobilization of the stress, but it will punch also. But in the case of end bearing column, so restraint will be provided from the end bearing soil. Okay, so now we have seen these different parameters, and we are going to have a certain equation for a settlement improvement factor. For settlement improvement factor, which are critical parameter which govern the design. So for a settlement improvement factor for fully reinforced stone column, okay, so these are the factor. These are S by D ratio, then it is a J, it is a modulus of reinforcement, diameter of the column, modulus of stone column material. So these are the certain factors which influence on settlement improvement factor. Okay, so we will derive here the equation for settlement improvement factor based on the graph theory. Okay, so here settlement improvement factor is being plotted for different S by D ratio. Okay, for different T value, there is a non-dimensional parameter. So non-dimensional parameter is equal to there is a previously we have seen J upon D into E. Okay, now here you can see here it is a relation between exponential relation between S by D and SIF. So if you go through the R square value, there is a very nearer to 1. That means there is a good correlation between SIF and S by D value. Okay, so here these are the equation in the form of exponential, and this is the form. Okay, so this SIF value depend on S by D with certain constant will be there. Okay, so now we need to derive this constant R1 and R2. So for this SIF, there is a for S T.625. This is the value of R1 and this is the value of R2. Now we will plot the interrelation between R1 and T. Okay, so here it is a T.625 up to the T10. Okay, so this is the value of T and this is the value of R1. So based on that, we have a equation for R1. There is a linear relation is being observed as R1 square R square value observed nearer to 0.98, and for R2 there is a logarithmic equation is being observed. Now put the value of this R1 and R2 in your SIF equation. Okay, so this SIF and S by D, and these are the our parameter, means input parameter, and this T is also our input parameter. So basically based on this equation, one can come to know based on the value of SIF. So as previously we have seen, so SIF means settlement of untreated and settlement of the treated ground. So based on this equation, one can calculate the value of SIF. Okay, you might have a value of spacing. That means based on your stone column, based on your stone column basic theory, based on the IS 15284. So you can choose the value of S spacing, and you can choose, you can come up with a diameter of the column, and T means your values of J, then values of E is required. Okay, so based on the properties of soil and properties of geosynthetic, you can calculate the value of T. So T is your nothing but J upon D into E. So E means your modulus of T surrounding soil, J means your stiffness of geosynthetic, and D means diameter. So if you want to know that I have an embankment of so much geometry, then soil having this much amount, this is the modulus of clay, and diameter of stone column and spacing is so and so. So you can calculate the value of SIF very easily based on this equation. Now, once you calculate the value of SIF, obviously you at the initial stage you will have a value of untreated ground. Okay, ground without any treatment. That is based on the routine consolidation theory. You can find out the settlement of the untreated ground. So once you know the value of SIF and this U value, you can find out the value of T. Means for a given embankment, what should be the future consolidation settlement going to have. Okay, so that can be predicted based on this equation. So if this treated after treatment, you get the settlement value or near future settlement value, so you can judge, you can play with this data. You can play with this data. That is, you can increase the value of J. You can, okay, so increase the value of modulus. Or you can increase the value, decrease the value of this spacing, and you can come up with certain value of embankment settlement. Okay, that is not having any significant deformation. So here in this table, for different S by D and different T ratio, this SIF value is being calculated and compared with previous projects. Most of the all projects are that we have taken here. That is German project and German case studies. That is this one is for there is a Airbus A380 production site. Okay, so you can compare the SIF value between these two. There is a actual case study and this equation. Okay, so this is the usefulness of this settlement improvement factor equation. So you can predict the real-time consolidation settlement of the embankment. Okay, so now it's I think almost 5 o'clock, and we have 3 and 4 points are still remaining. So I will just need to go hurriedly. Now here, this is the related to laboratory model test. Okay, how to carry one can carry out the model test in the laboratory and do the numerical simulation of the same for a reinforced stone column. Okay, so those going to pursue a PhD in relevant area, for them it can be useful. Now, when you reach for the laboratory model test, so you might require certain model tank, you require certain stone column material. I mean, then you need to choose the diameter of the column. Okay, so you should have a certain basic background of that. Means in the laboratory view, which diameter you should have to choose. Okay, whether it is 50 mm, 100 mm, 70 mm, 200 mm. Okay, so this diameter, length, how you can choose. Okay, so that is based on the unit cell concept. Okay, so this theory is based on the unit cell concept, in the sense in the field you will have a number of column. Okay, in the site you will have a number of column, but each column is surrounded by number of column. So basically what you can see here, that this particular column that is surrounded by number of column. So this column, you see, settlement predominantly will be vertical. Settlement predominantly will be vertical for this inner column. Okay, so it is constrained. Basically it is a constraint with the number of column, constraint with number of column. Okay, so it will settle predominantly vertically. So you need to apply just vertical load for on single column. That is a, you are modeling the inner column, okay, not the outer column. If you have embankment somewhat like this, so this unit cell theory in the sense that you are modeling this one column, okay. So if you, this column will behave differently, okay. In this column, that particular middle of the embankment, this region column, so it will settle mostly vertically, but at the toe of the embankment, this column will get bulge also, lateral deformation also there, okay. So this unit cell concept is applicable for this particular middle column, okay. Now that is a that one which having a more vertical load, okay. Now in this particular paper, this certain similarity concept is given, means L by D ratio in prototype is between 5 to 20. So you have to take L by D ratio in the model test also in that particular range. Okay. Then small d by capital D ratio in the sense the diameter of the stone column to the diameter of the particle size, mean particle size, there should be range between 12 to 40. Okay. So this is the field, means whatever the field non-dimensional parameter. So similar methodology we have to adapt. It means you need to scale down your geometry, okay, but that value should be range as in the field, okay. So that is the thing, okay. And obviously geosynthetic which is available in the field, it might having a, as we previously we have seen, that is a J1 modulus vary from 1000 to 8000. So you can't directly take that values, I mean that you can't take that geosynthetic directly in the laboratory, because in the laboratory stresses are less compared to field. So obviously you need to have a scale down every material, okay. So this is the thing, that is this is the model tank and schematic diagram of the this particular tank, okay. So this is the length of particular tank and the dia, and you, if you want to observe the settlement, so obviously you should have a dial gauge or displacement transducer, or, and for the load point, perspectively point, you should have a load cell, okay. And this is the varieties, means this is the plate load test on clay, then ordinary stone columns without geosynthetic material, then the reinforced stone column with different type of reinforcement, net, non-woven, woven. The number of plate load test was conducted. This is the property of clay. You can see here that it is a as per it is a CL category soil, okay, and having a on-drain cohesion value, it is around 8 to 10 kPa, okay, and the degree of saturation is observed around 0.88, okay. So this is the grain size distribution for the clay and stone sand. Sand means for the stone column material. For the stone column material, sand is being taken because there is a large size material. You will have a diameter of the column, say for example 50 mm. So you can't take the stone column material 20 mm or 10 mm. Okay, so you have to scale down your grain also, stone, I mean your material also. So that's why sand is being used. Okay, so this is the river sand being used, having a compacted density unit weight at the 16. Okay, having a poorly graded sand, and for each material you see this modulus is being also find out, because at the later stage for numerical analysis we require modulus of elasticity value also. Now we can see here that is a in the field you will have a geosynthetic of this kind, having a tensile strength geosynthetic stiffness around 1000 to 5000 kN per meter. So but you can't use directly that material, okay. So here this first one is the geo net, means there is a mosquito net that one can use, that is having a very minimum tensile strength. Then in between there is a non-woven geotextile. So non-woven geotextile also having a not strength and the tensile strength. It is basically used in the field for the drainage perspective. Okay, then this is the woven geotextile, and it is a being sleeve is being formed, cylindrical sleeve is being formed by using epoxy. Okay. Now this is the tensile strength of different geosynthetic material. Stress versus tensile load versus strain graph is there. So you can see here this particular net, okay, having a tensile strength, and that is a woven geotextile. So that is a very minimal to where higher range that geosynthetic is being taken. So there is a very wide range material is being taken. So when you prepare the clay, you see, take care that water should be evenly distributed. So what happened in the before a day, okay? So you keep clay and soil, clay and submerge this clay with water and kept for 24 hours. So what happened? That water will be mixed properly with clay material. So, okay, and you can just manually you need to certain mark will be there. So you just mold the soil just at the 50 mm interval, just 150 mm for a 50 mm. You will have a density and that particular material thickness. I mean that material layer thickness 50 mm. So for that, what are the what should be the amount of soil you require? So that much amount of soil should be taken out by weighing, and you just keep in particular tank. Now here you see for this technique displacement method is being used. So here this particularly pipe is being there. It is a pointed pipe is there. Okay, so it is being kept, and the sleeve is being surrounded to this particular casing, and it is being installed at particular depth. And after that, stone mud sandy soil is being kept, and stone column, this column is being compacted. But you see, in this also, it is kept in mind that compaction should be, I mean, should be evenly in the sense that every time drop of hammer should be at particular depth, from the particular depth. So for that, certain mechanism is being done, that every time the depth that is that hammer, this rod will drop from predefined depth only, and that depth, that lift, that height will be constant. So there will be uniform, you see, density will be reached. Okay, and then you can have a load cell and agility, and after you see this all load is being applied, okay, load settlement curve is being done. What happened? What to do? You can take out this sand very carefully, or otherwise what you can do, you can penetrate this there is a plaster of Paris in this stone column. Okay, so it will get penetrate in particular this material, in the stone material, because it is a porous. Or you can take out carefully this stone material, and you can pour this plaster of Paris. So after a day, what happened? This plaster of Paris will get hardened, and whatever the shape of bulging, so that's bulging you can observe, that bulging shape can be observed. Okay, and after you see the laboratory model is plate load is being simulated numerically also. So how this behave, means failure is observed, whether failure being observed in the laboratory and numerical, based on the numerical analysis, is identical or not. Okay, so that is being done. So this is a single stone column. Okay, so you need to take care while doing the numerical modeling, that very often it is observed that you observe certain experimental value, and you do numerical analysis once, and you observe that you don't get the match between this experimental value and numerical value. The thing is that you have to take care for the this meshing in the sense that you have to go for the convergence analysis. You have to go for number of meshing, means in particular plexus you will have a mesh configuration from very coarse to very fine. So you have to go for number of meshing Okay, and you have to simulate your result, numerical results with experiment. Okay, so you can see here the meshing which is adapted for the stone column. It is a very fine mesh and compared to surrounding soil. So the thing is that the concentration of the load will be there on stone column. So obviously there should not be any node which any nodes should not be missed where there is a maximum node, maximum load is there. Okay, so you can see here that effect of this geosynthetic reinforcement. So you can see that the stone column which is being cast through POP, plaster of Paris. So you can observe this bulging. You can see here clearly. But in the geosynthetic reinforcement, you don't have a observe appreciable amount of bulging. So by you see doing filtering the POP, you can observe this kind of lateral deformation, bulging that is observed in the beneath the ground, beneath the soil. Okay, so this is the thing that one can go through this material. Okay, so you can see here this clay, observe this soil, I mean load settlement response for clay. Okay, so it is suddenly you can see here is just punching is being observed. Okay, it will get punched, means there is not much more load carrying capacity observed. So even you can see here with this ordinary stone column, it means R means reinforced stone column. Okay, with experimental and numerical value. So you can see here at the 50 mm settlement also this value, there is a load carrying capacity value does not get increased, but you can see here the large amount of increase in load carrying capacity. Okay, so this is the thing with means compared to ordinary stone column and reinforced stone column, with reinforced stone column is much more higher carrying capacity. It is around 4 to 5 times compared to ordinary stone column. Okay, so same thing you can see here. So whether this kind of bulging is being observed, that is in experimentally, so you can see in the numerically also. So at that particular depth, at the top level, you can see here at the top level. So you will observe this kind of bulging. There is a radial contour is there. Okay, shading is there. So this is with respect to ordinary stone column, and this is with respect to reinforced stone column. So the thing that we need to observe that you can see here that with this ordinary stone column, you see bulging is up to this much depth only. Then after you see there is no bulging observed. Maximum bulging is more, but after that there is no bulging. That means whatever the settlement that we observe, so what that will settlement, say for example vertical settlement that will observe. So due to that, what happen, that stress which is mobilized, it will transfer horizontally. So that's why you will observe this kind of lateral deformation at upper depth. But with respect to this reinforced stone column, you can see here there is a lateral deformation observed. Is maximum is much more than ordinary column, but lateral deformation goes beyond that level, beyond this level. That means what happens? The stress will mobilize at a deeper depth while will having a reinforced stone column. Okay, so what happens? We can take advantages of this end-bearing soil. We will have advantages of this end-bearing soil. Okay, so that is the thing. Means if you plot settlement versus depth, okay, so what happened with ordinary stone column and with respect to reinforced stone column? So most of the settlement will occur at particular this depth. Okay, but when we have a reinforced stone column, what happened? Settlement will reach up to the particular this level. That means stress will mobilize at a deeper level. So due to that, what happened? Bulging will not occur more in reinforced stone column, but here most of the stresses mobilize at an upper level. So that's why you will have a more bulge compared to this reinforced stone column. Okay, so that's why this ordinary stone column much more depend on surrounding soil property. Okay, so now likewise you see different parameters being studied at the laboratory level also. Effect of diameter of the column. So you can see here, if you have a smaller diameter of the column, you will have a more stress. You will have a more stress because as we have seen the Hooke stress theory. Hooke stress theory, there is a stress stress is inversely proportional to diameter. That means if you have a smaller diameter, there will be a higher stress. That will be higher stress, higher confining stress. Okay, so in the field, if you go with higher lower stone column, then you have to provide number of stone column. And if you go for the bigger diameter of the stone column, the number of column will be lesser. Okay, so with lower stone column, confining stress will be more compared to higher diameter stone column. Okay, so this is the interesting phenomenon that can be observed through the laboratory and as well as the numerical analysis. Okay, so same thing for non-woven and woven geotextile is there. And obviously, as vertical settlement, if it is vertical settlement is more, that means higher stress will be mobilized. Higher stress will be mobilized means load carrying capacity will be more. So that is the graph will show here that stress with 50 mm settlement is more compared to 25 mm settlement. Okay, and again these are the deformed shapes of this reinforced stone column and non-reinforced stone column. So you can, this is the width for a 75 mm diameter ordinary column, and this is with 75 mm diameter reinforced stone column. Okay, different graphs, and again this is with for a bulging of the column. So you can see here for a ordinary stone column, both 50 mm 75 mm diameter column bulge much more. It might be behave more or less same, but with respect to reinforced stone column, you will have a much lateral deformation. Okay, and this reinforced stiffness is also again having the same phenomenon, means higher the stiffness, more will be the load carrying capacity. Okay, these are the contours, then deformed shapes. This is with respect to lateral deformation. Okay, now this is interesting one. In the embankment, what we have seen that reinforcement length does not having any unique value, means you don't restrict reinforcement length up to 4 times diameter, up to 5 times diameter. But here you can see here that in this graph, this is a reinforcement length for different diameter and reinforcement length. So you can see here that 50 mm diameter and 75 mm diameter. So for example, here 50 mm diameter column. As you go for the reinforcement length from this to 225 to 450, means from if you go up to the 4.5 times diameter, if you provide the diameter reinforcement length up to about 4.5 times diameter, so there is not appreciable amount of increase in load carrying capacities also. Okay, so in this one can say here, so based on this study, one can say that for a single stone column, if you analyze, in that case previous conclusion is valid. There is a up to the 4 times diameter reinforcement length is enough, significant reinforcement length, there is a load carrying capacity can be observed. Okay. So that is okay with a single stone column. And you can see here that is when you have a partial reinforcement length, so there is a certain subsidiary bulging will observe at a particular junction. So you can see here. Okay, so this is the reinforcement portion and this is the non-reinforcement portion. So obviously at this location bulging will be more, but there is a subsidiary bulging will be observed at the junction of unreinforced and reinforcement portion. Okay, with respect to woven geosynthetic. So you can see here there is a reinforcement length 225. This is 450 means end bearing, So you can see here reinforcement line 225. There is a small reinforcement line is being provided. So indeed, in that case, you will have a bulging will be at the junction of reinforcement and unreinforcement portion also. So and the stone column length is same behavior as previous study. Okay. So this is the you can see smaller L by D ratio, higher L by D ratio. So even in the smaller L by D ratio for this study, you will bulging is being observed, not a shear failure not observed. Okay. So this is the same with respect to lateral deformation. Now, whatever you see, even though you compare with the numerical analysis, you ultimately for the field perspectively, when you go design the stone column, obviously you should have a certain closed form solution, certain equations should be there. Okay, so based on the guidelines of this paper, and again with respect to IS 15284, you can use this equation, comparison of ordinary stone column, that is sigma R naught plus 4cu Kp column. So this Kp column means passive earth pressure coefficient. Okay, sigma R naught means confining pressure. Okay, so this you can come up with this sigma V naught means vertical stress. There is a gamma into H. Okay, so you can calculate the value of sigma R naught and put the value of here sigma V. Sigma V means load carrying capacity of the stone column. So you can come to know this stone column bearing capacity, single stone column. So based on the if you have a number of, I mean, just like a storage tank is there, that is a one column provide this much stress. So based on the this stress, you can come to know the load taken by one column, and subsequent based on that for this total LNG storage tank total load, how many number of column you require. So you can easily come up with these numbers. Okay. Now with respect to reinforced stone column, now in the previously equation is same, but here this additional value will parameters will be there. So that is called lateral confining pressure or hoop stress provided by this geosynthetic material. So this is the thing. This is the thing is there. So it will provide additional confining stress, additional lateral stress. Okay. So that is for that there is a certain equations are there based on the strain, there is a displacement transfer on the stone column. You can find out the hoop strain, and from that strain you can find out the what is the tensile load mobilized, actual mobilized. Okay, so that you can find out and you can put the value here and you can find out the value of this confining stress. So you can see here this value, PC value, compared to this influence of this cohesion and influence of confining stress provided by this soil. So you can see this combined two value, there is only 37 kPa only. But with respect to this geosynthetic material will provide confining stress up to 2 times compared to just simple compared to just soil material. Okay, so you can compare the same with this analytical equation also there. Okay, so we will just a couple of minutes remaining, 5-10 minutes remaining. So I think we will go readily with field load test. So obviously you see whatever the laboratory scale you do, but you see that is at a small scale you do, and you will have at this small scale you will have advantages of material and preparation of the installation of the column and all that can be possible. So you will have a good conclusion, but ultimately the thing you will going to have on field. So obviously you should have try in the field also. Okay, so this is the location of stone column, reinforced stone column construction, very near to this creek. That is a creek is very near here. So this is the you can see here. This is the area that is a very soft material is there below the ground itself. Okay, so you can see here the up to the depth of 4 meter actually the SPTL value there is a very near to maximum 5 value up to the smooth there. Okay, then after the SPT value is more because we have a plastic silky clay, but at that particular up to the 4 meter to 5 meter depth we will observe non-plastic silt, there is a blackish. Okay, and this is the ground material characteristics. Okay, the sand means the sand column. Basically here instead of stone column, sand column is being used. Okay, because we need to go for the geotextile material. Okay, so this is the property of sand. Okay, now here you can see here there is a geotextile sleeve is being formed, and tensile strength of that particular material, two variety of geosynthetic geotextile is being used. So you can see here it is very lower value and upper value. There is upper value around 450 kN per meter. Okay, so this is the construction method. You can see this is based on the replacement method, and all the SPT that is a while I have previously told there is a simple tripod is being used. Okay, and here this geotextile is being actually being kept at particular level, while just like here. Okay? When you insert the geotextile at the inner of this casing pipe, so at the upper level it should be tied, otherwise it will get sink in the ground. Okay, so as you compact, it will take the form of this circular cylindrical shape. Okay, so these are the just certain background related to loading arrangement, and all this displacement. There is a dial gauge and pressure cells are there. Sorry, this loads pressure pump is there. Okay, so you can see here there is a without improvement and with improvement load carrying capacity. Okay, and later on it is compared with the analytical solution also there. Okay. So the analytical solution that is we have previously seen. Okay, and again same methodology is being applied, and there is a good comparison you can see here with experimental and analytical. You will have a good comparison being observed. Okay, so whatever the conclusion which is be derived from the laboratory, so does it serve in the field or not? Okay, so that is required to compare. So as previously the main research that is right now going on is regarding the reinforcement plan, means optimization of reinforcement plan. So up to the which how much depth length one can go for. Okay, so for embankment point of view, there is not an optimum length right now reached, but for the column which is having a purely vertical load. Okay, so in that case the reinforcement length here based on the particularly field study, so it comes out of around 4 times diameter of the column. So okay, so around 4 to 5 times diameter, 4 to 4.5 times diameter of the column. So this is the final conclusion one can say, that is based on the laboratories test and numerical analysis, and finally based on the field study. If you want to go for the just as a bearing capacity point of view, stone column, there is a beneath the raft or beneath the or storage tank, so where you will have just a vertical load only. Okay, so in that case this conclusion can serve, that is a you can go for the reinforcement length up to the 4 to 5 times diameter of the, so on an average 4.5 or 4 times diameter of the column. So that can be enough. Okay, so but that is not in that is not a thing for embankment point of view. So that we have seen. Okay, so one can go for this much depth of the length of the reinforcement length. So that you can see here. There is from no reinforcement length up to the this 4 times reinforcement length. Okay, you can see here it is a, then after you can see here there is a from this to this level there is a and fully reinforced length. Okay, this is 4 times diameter, so this value does not get changed much. Okay, so you will get significant reinforced increase in load carrying capacity. Okay, so this is the thing, and we have a right on time. So thank you very much, and obviously we might have a certain question. Okay, so we'll take few question, not a few, but whatever the question we will have, we will take it. Okay.
Hello. Supla sir, have you raised your hands? Do you have any questions? You can open your mic and ask the questions. Or otherwise, the chat box is there, WhatsApp box is there. If you have any query, you can raise the questions to the sir. So all the participants, please feel free here to ask the questions. So there is no questions from the participants. Yes, the raised hands are there. Does anybody? Yes, ask. Those who are raising the questions, please allow him mic.
Okay, you can unmute,
Supla sir,
unmute also.
Supla sir, you can unmute and please share your voice over here. Those who want to, because you have raised your hands. So there is no questions from the participants. So on the behalf of the participants, I thankful to Dr. Tandel sir to spare their precious time and give the valuable knowledge related to this column over here. So thank you very much, sir. Now all the participants are requested. The second day, all the 3 sessions are over. The third day, the first session will be started at 10 a.m. early in the morning. So we will meet tomorrow. Thanking you. And any kind of difficulty, any kind of questions, you can directly contact over to the WhatsApp, or you can personally to the WhatsApp also. Thank you.